Now we want to talk about dipolar field perturbation and magic angle spinning. We learned that peaks are broadened when the T2 are short. And the reason for a short T2 is because there are many different local magnetic fields. A common problem in solid samples is the enormous perturbation from local dipolar fields, which cannot be averaged out by molecular motions like in liquid. For a nucleus which is a magnetic dipole, say the mu I in the graph, the strength of the dipolar field due to a nearby nuclear magnetic dipole, mu J, is directly proportional to bracket 3 times cosine square theta minus 1 bracket times cubed r, where r is the distance between the two dipoles, which is the magnitude of the vector rij in the graph. And the theta is the angle between the rij and the line about which mu I precesses, which is parallel to B0. Here we have 4 concepts: Ri, Rj, Rij, and theta. Apparently from the formula, this dipolar field can be diminished if 3 cosine square theta minus 1 equals 0, which means that theta should either be approximately equal to plus or minus 54.74 degrees or 180 plus minus 54.74 degrees. These are the magic angles that can make the dipolar field vanish. Technically, this is achieved by magic angle spinning, that physically spins a sample a few thousand to 10 of thousands hertz about the magic green line that is tilted about 54.74 degrees, which is theta m in the graph, from the direction of B0. As a result, all R's for the mu's are averaged to RM's on that line, where M's are for magic angle. For example, the spinning Ri is averaged to RIM, represented by the short purple vector in the graph. And the spinning Rj is averaged to Rjm, represented by the long purple vector in the graph. Therefore, Rijm, represented by the orange vector in the graph, also lies on the magic line. With this kind of spinning, all the dipolar field's perturbation are diminished. Now it's about the Bloch equations, which is a set of ordinary differential equations that is often used to perfectly describe the NMR relaxation of a single spin. To understand the great idea behind Bloch, who won a Nobel Prize for his work on NMR, we should learn how to understand the equations. If you open your mind and follow my statements, I'm sure you should be able to pick up something. First, let's have a look at a definition. The derivative of x with respect to t is simply the limit of delta x divided by delta t when delta t is approaching 0. What is the delta t? It is simply an interval of time. And delta x is the difference of x during that interval, i.e., delta x is what happened to x during that time. To understand a differential equation, we often change the d's into deltas. For example, the first equation on the left then becomes delta mx divided by delta t equals minus 1 over t2 times mx minus omega j times my, where delta mx is equal to mx at time t plus delta t minus mx at time t. Then, by shifting the mst and delta t to the right-hand side, we have the second equation on the right, i.e., mx at time t plus delta t equals mx at time t minus 1 over t2 mx at time t times delta t minus omega j my at time t times delta t. In other words, mx at time t plus delta t equals mx at time t minus the part that decayed away during delta t and the part that changed to my during delta t. Similar explanations can be made for the other two differential equations on the left. Note that you can replace 1 over t2 and omega j in the equations with any symbols, say a and b, and then the solution to the equation will tell you exactly what they are. This is the beauty of the idea. We have learned before that mx and my are oscillating time domain functions that decay exponentially with time. Now we want to tell you that they can be combined to become an entity such that mxy is equal to mx plus I my, where I is the unit for the imaginary part of a complex functions, i.e., mx now is the real part and my is the imaginary part of the function. In fact, to present a complex function, we also use two perpendicular coordinates that are similar to the x and y axes in the Eulerian frame of reference. With the introduction of mxy, the block equations can be beautifully simplified, as explained on the next slide. Here are the simplified block equations. The first equation is for mxy, which can be proved by multiplying an I to both sides of equation 2 prime, and then adding it to equation 1 prime. With a bit of rearrangement, you should be able to get the simplified equation for mxy, i.e. equation 1. Try to do this at home. It is a good exercise for you to build up your confidence. You're welcome to ask me any question if you got stuck. It's only an algebraic exercise, nothing advanced. You may wonder why equation 2 got an extra m0 on the left-hand side. It can be added there because the derivative of any constant is 0. And m0 is a constant, not a variable. With the m0 added, both equation 1 and 2 then have exactly the same format. And it is a format that can be easily solved, as shown below, i.e. the derivative of y with respect to t is equal to c times y, where c is the constant. For equation 1 and 2, the y's are mxy and bracket m0 minus mz respectively. And the c's are bracket minus 1 over t2 plus I times omega j and minus 1 over t2 respectively. The general solutions are y equals to a times e to the power of ct. The proof is easy. By taking a derivative of the solution y with respect to t, you then get dy over dt equals dA times e to the power of ct over dt equals a times e to the power of ct times c. And it is equal to c times y, because a times e to the power of ct is y, which is what equation 1 and 2 are. If you replace the y's and c's with proper terms in the second statement. Therefore, mxy is now equal to a1 times e to the power of ct, where c is equal to bracket minus 1 over t2 plus I omega j. And for equation 4, we got m0 minus mz equals a2 times e to the power of ct, where c is minus 1 over t2. Note that e to the power of a plus b is equal to e to the power of a times e to the power of b, which is how equation 3 looks like that. Now we learned that with the simplified equations, the solutions become just that simple. Now we want to have a further look at the solution to the block equations. The solutions presented in the last slide are called general solutions. For every set of initial conditions, you get a set of particular solutions, which describes the status of the variables at time t equals 0. In this case, It is the status of m0 immediately after pulsing, which has three components: mx0, my0, and mz0. And you can combine the conditions for the mx and my into one complex condition so that mxy0 equals mx0 plus I my0. In other words, the mx0 is the real part of mxy0, and the my0 is the imaginary part of mxy0. Say if a y pulse was applied, and it tilted m0 down an angle from the z-axis, say beta degrees, as shown in the graph. Then the initial conditions are mx0 equals m0 times sine beta, my0 equals 0, and mz0 equals m0 times cosine beta. If the pulsing angle beta is equal to 90 degrees, then cosine beta equals 0 and sine beta equals 1. The conditions are further simplified to mx0 equals m0, my0 equals 0, and mz0 also equals 0. And hence the mxy simply contain a term m0. Substituting these with t equals 0 into the general solutions, you will then get A1 equals A2 equals m0. And then, substituting the value of A1 and A2 into the general solutions, you get the particular solutions, i.e., mxy equals m0 times e to the power of I omega jt times e to the power of minus at, and it is also equals to m0 times st times wt, where the st, wt, and a are defined below. We also have mzt equals m0 times bracket 1 minus e to the power of minus t over t1. We will call st the spinning factor, wt the waning factor, and a the decaying exponent, respectively. And you will soon understand why we call them that way. This slide is just a continuation of last slide. Now we want to talk about the meaning of the spinning factor St. It is immediately clear as soon as we expand it with Euler's formula, which says that e to the power of I omega jt equals cosine omega jt plus I sine omega jt, which is equivalent to the equation for the rotating B1 that we learned before. Indeed, on a complex plane, where the real axis is perpendicular to the imaginary axis, we get a full circle in 1 second if omega j is equal to 2 pi radian per second. Because 2 pi radian per second is 1 hertz, which is 1 cycle per second. Increasing time t to a larger number, we get the same circle again and again, which means something spinning. Now we see that on the XY plane, nuclear magnetic moments really spin like a wheel. This is a different concept from the 3D precession of nuclear magnetic moments. Substituting the Euler expansion above into the particular solution for mxy on the last slide, we then get the equation that describes the oscillation of mx and my, i.e., mx equals m0 times cosine omega j times e to the power of minus t over t2, and my equals m0 times sine omega jt times e to the power of minus t over t2. Both of them contain an amplitude m0, an oscillating factor, either cosine or sine, and a decaying factor, e to the power of minus t over t2. The rest of the contents on this slide are very obvious. Here is a summary for the last few slides. In brief, NMR signal is the multiplication of m0, which is the macroscopic nuclear magnetic moment, times a spinning factor times a waning or decaying factor. It is simple and very easy to be remembered.